Okay, so please download simplependulum.zip file, and I would work out the problems on Matlab, and then I would show you how to do it using Matlab. Yeah, so what I was trying to say here is please download and extract simplependulum.zip file from Canvas. And I have extended the deadline. And today's lesson is super important. Zip file is not for the homework, but this will give you some background on how to solve the homework file. So what is the purpose of today's lesson? Today's lesson is using Matlab to find differential equations of motion. And solve those differential equations of motion and solution. And this lesson would continue for at least next 3 to 4 lessons. So we would actually repeat this exercise, and we are going to study progressively complex system all the way to the systems shown in homework 4, assignment 4, and assignment 5. So please download the zip file, extract, and then open the Matlab. Now what I want to do is, I want to first take a very simple example of 1 degree of freedom robot. So this is a simple 1 degree of freedom robot. And I'm going to assume that this robot has mass m, the length of the robot arm is L, and what I want to do is, I want to derive the equations of motion. Now for a second, I want you to take a look at this robot arm from top. And you would realize that this robot arm, when we view from top, is something like a simple pendulum. So this is a simple pendulum. This pendulum has some mass m. So this is the mass m. This is at length L. And what I want to do is, I want to derive the equations of motion. So the first objective is to derive the differential equations of motion for this simple pendulum. There are 2 ways to derive the equations of motion. One approach is using Newton's law. So what is Newton's law? Newton's law is force is equal to mass times acceleration. And that can be written as torque is equal to mass moment of inertia multiplied by angular acceleration. So this is torque. This is mass moment of inertia. And this is angular acceleration. So what I'm going to do is, first I'm going to derive this equation using Newton's law, and then I will talk about the Lagrangian approach that we talked about briefly in last class. First and foremost, let's identify the forces on this pendulum. We have m times g, which is the self weight of the pendulum. I'm going to call this point O, or the origin. And please note, if this angle is theta, this distance is L sine theta. Now, if I want to apply the Newton's law, torque is equal to I times alpha, then please understand, look at the direction of the torque. This torque, as you can see, is going in clockwise direction. So curl your fingers in the direction of the torque. And let me show you the coordinate system that we are going to use. So you have X, you have Y. Use the right hand thumb rule and you will see that the Z is coming out of the page. So Z is coming out. So if you look at the direction of the torque, curl your fingers in the direction of the torque and you'll realize that this torque is negative. So I'm going to write this down as M times G L sine theta. Please note why this torque is negative. This torque is negative because when you curl your fingers in the direction of the torque, this is the direction of the torque, curl your right hand fingers in the direction of the torque. Can you notice your thumb is going inside the board or inside the page? That's why this is negative. Is equal to I is the mass moment of inertia. Mass moment of inertia we talked about in the last class. I is mass times the radius of gyration square. So the radius of gyration is L. So this distance M L square is the value of I multiplied by angular acceleration, so which is the double derivative of theta, so which is theta double dot. So what that means is this equation can be written as ml square theta double dot plus mgl sine theta is equal to 0. And this is nothing new. Most of you have seen this in vector mechanics, or for that matter, statics and dynamics. And this equation actually simplifies to G over L sine theta is equal to 0. So this is the differential equation of motion. What do I mean by differential equation of motion? So please note, theta is function of time. This is a function of time. And the solution of this differential equation is going to show me a functional relationship between theta and time. So as time goes on, how does theta change? Okay, now as you can see, this process is not straightforward to apply inside a computer software system. So basically, how would we automate this procedure? So here, the Lagrangian formulation comes to rescue. So I'm going to show you Lagrangian dynamics. The beauty of Lagrangian dynamics is you do not have to worry about the signs or the direction of forces. So what is the procedure here? The procedure here is first find out the equation for kinetic energy. The equation for kinetic energy is 1/2 mv square. So the equation of kinetic energy is nothing but 1/2 times mass. Velocity is this guy. So the velocity here is theta dot times L. So which is going to be theta dot L square. So the kinetic energy is given as 1/2 m L square theta dot square. Everyone clear about the kinetic energy? I'm going to go very slow because please understand, if you don't understand these simple concepts, the next material is going to be very difficult. So I found out the kinetic energy. Now what I want to do is I want to find out the potential energy. So the potential energy, I'm going to consider datum over here. This is my datum. Potential energy, PE, is nothing but M times G times H. Now, as you can see, this distance from here to here is L cosine of theta. And we are going below the datum. Can you see the datum is 0? This is the point where my potential energy is 0. So datum is where my potential energy is equal to 0 at the datum. As I'm going below datum, I would have negative potential energy, which is M times G, and H is L cosine of theta. Everyone understood this? Let me just expand this and write this down as L cosine of theta. This is nothing but H, and this is below datum. Any questions in kinetic energy and potential energy? Now, at this point, let me define a super important concept called Lagrangian. L is called Lagrangian. And Lagrangian is very simple. Kinetic energy minus potential energy. So kinetic energy is 1/2 m theta dot square L square minus potential energy is minus of mg L cosine of theta. Now please understand, I'm gonna derive this for only this problem. For next problem onwards, we are going to use Matlab. But in the very first problem, I would like to derive the equations and show you that the equations that you get running the Matlab code are exactly the same. So I got the Lagrangian. Now I have to use something called as Lagrangian equations. So this is the new part. And this Lagrangian equation is given as, and remember this, is d by dt of partial L divided by partial theta dot minus partial L by partial theta is equal to external forces F bar. And remember this equation. So what do I have here? This is the velocity term. This is the angular displacement term. So what I'm going to do is I'm going to evaluate these terms on the side. So let's start with partial L by partial theta dot. What that means is theta is equal to constant. It's a partial derivative. So partial L divided by partial theta dot. Can you see that this equation becomes m L square by 2 theta dot. So which means I cancel this out and I land up with m L square theta dot. This is a partial derivative. Next, I'm going to do partial L by partial theta. And partial L by partial theta, which means theta dot is equal to constant. And when I do that, please note the first term is going to give me a 0. Second term is going to give you a minus m g L. Derivative of cosine theta becomes sine theta. And this is the solution, minus mgl sine theta. Now I'm going to substitute these values. So check this out. This term is this guy, and this term is this guy. So this equation is going to become d by dt m L square theta dot minus mgl sine theta. And please note, in this problem, there are no external forces. So I'm going to write this equation is equal to 0. No external forces. How would you find F bar? F bar will be found using method of virtual work. So the technique that we discussed in last class will be used to find this method of virtual work. But if you look at this particular pendulum problem or the robot problem, there are no forces, no external forces. So I'm going to write this down, external. So this can be simplified. Notice this is d by dt. M is a constant, L square is a constant. So I'm going to have an equation ml square theta double dot plus mgl sine theta is equal to 0. And I can cancel out ml and I get equation theta double dot plus g over l sine theta is equal to 0. Now this is super duper important. And before I go programming this inside Matlab, I just want to quickly recap. So in today's class, we are going to look at how to formulate the differential equations of motion and how to solve differential equations of motion. So the first part is how do we formulate? There are two ways to formulate a differential equation of motion. One is Newton's laws. Force is equal to mass times acceleration, or in rotational coordinates, torque is equal to I times alpha. So this approach shown over here is Newton's law. So this approach over here is Newton's law. And as you can see in Newton's law, first and foremost, you have to draw something called as the free body diagram and use that free body diagram, find the forces, and then equate the torque value is equal to I times alpha. On the other hand, second approach, and this is the preferred approach, is using Lagrangian dynamics. And the beauty of Lagrangian dynamics is once you find out the kinetic energy, once you find the potential energy, you just have to use this equation, the equation that is shown over here, this equation, star equation. And this equation, once you apply, then that gives you the differential equation of motion. Everyone understood this? Any question? Now the question is, how do we solve this differential equation of motion? Please note that this differential equation is nonlinear. Why it is nonlinear? Because sine theta is a nonlinear function. But for many a times, we can convert that into a linear approximation. What does that mean? Oh, bear with me for a minute. The Zoom crashed. So okay, can you hear me? Awesome. So we have to thank Zoom for this interruption. But what I'm trying to say here is for theta values less than 17 degrees, the radian of theta is equal to sine theta. So the linear approximation works. What that means is for small values of theta, for small theta less than 17 degrees, I can rewrite this expression theta plus g over L theta is equal to 0. Now, this equation needs to be solved in Matlab, or in certain cases, simple equation can be solved analytically. But if you want to solve this equation in Matlab, specifically numerically, then we need to convert this into set of first order equations. And again, we are not going to do that for all the problems. Matlab will do this for us. But I'll tell you what this means is we want to write this equation, a second order differential equation, into two first order differential equations. So how does this work? So I would write this down as theta dot. I'm going to use displacement and velocity, take the derivative and write this as a matrix equation. And you would notice that this equation gets written as 0, 1, then minus g over L 0. So if Matlab wants to solve this, then we need to supply the equation, equation like this in the Matlab solver, which is ODE 45 or ODE 23 and so on. Now this is called as the state space representation. State space representation. So what we are going to do, and from this point, I'm going to go to Matlab, and actually I would show you how to code this inside the Matlab environment, and not only to come up with this differential equation, but find a solution. What that means is I want to find out theta as function of time, and I want to find out theta dot as function of time. So this is meant by solution. Any questions here? And then I would show you how you can simulate this using Simulink. So first we'll use Matlab, then we will use Simulink. And if some of you really want to try, what you can do is you can take that Simulink solution and feed that to animation routine inside Matlab, and you will see the pendulum, actual pendulum running. So let's, if there are no questions at this point, I would like to switch to Matlab. Are there any questions at this point? If there are no questions, I'm going to share my screen and we are gonna go to Matlab. So at this point, everyone, please open the simple pendulum .zip file, and I would actually share my screen. Can you see my screen? Okay. Now I want you to look at simple pendulum, change the folder, and then open the first file, equation, run this first pendulum. Okay. So now step number 1, this equation, this is the main file where we would write down our kinetic energies and potential energies. And I want you to open Euler-Lagrange.m. This is the file that will take the input and derive the equations of motion, solve equations of motion, and create a Simulink file that can be integrated for animation or for graphic visualization or for control. So let's quickly look at this code. This is the code. So Euler-Lagrange, the input is L, X, Qi, Qe, R parameter and various argument. So Lagrangian, please note, is L, which is T minus V, where T is the kinetic energy and V is the potential energy. Now, if you go down, first and foremost, I want you to understand that the Lagrangian needs to be defined symbolically in terms of generalized coordinates and system parameters. What do I mean by that? Please note, for our pendulum problem, you have something called as theta and you have theta dot. You need theta for potential energy and you need theta dot for kinetic energy. Everyone understood this? So theta and theta dot are the generalized coordinates that they need to be defined as symbolic variables. Then Q's are the vectors of generalized forces. So F bar that I wrote is nothing but the generalized forces. Qi are the internal forces, for example, damping. And Qe are the external forces that do not depend upon generalized coordinates, but you can treat them as some sort of a controller force. Now, if you go down the code, it can generate M file. It can also generate a Simulink file. And basically, you can use this M file to run the numerical simulation. You can use the Simulink file again to run the numerical simulation and integrate with the control system block set or any other block set that is available inside the Simulink. There are some examples that are given over here. So what I'm going to do is, first and foremost, I won't go through how the code is written, but the idea is a symbolic variable is defined. From that symbolic variable, actually the equations of motions are formulated. Those equations of motions are differentiated exactly the way we did. And finally, everything is simplified. And then finally, the vector is written. And this code is actually written by MathWorks. So this comes directly from MathWorks. Any general questions about the code? So we are going to use this function again and again to derive the equations of motion for simple pendulum, double pendulum, robot arm, or maybe some other complicated multi-body dynamical systems. Okay, before I proceed further, any questions in this code? No questions? I'm looking at the chat window. Okay, now let's see how would we solve the pendulum problem. I'm going to go line by line, so follow my lead. Yes. Can you see my screen, or do I need to zoom in? So I would just go ahead and increase the font a little bit. So first line is symbolic variables. So these are TH is theta and THD is theta dot. So TH is the theta and this is theta dot. Everyone understood this? Then since I'm going to solve this equation numerically, I'm going to supply the value for gravity. G is equal to 9.81. I'm going to assume mass is equal to 0.1 kilograms. L is going to be 1. And this K is actually not used. So first, this is, and please note, this is exactly how the code must be written. If you write the code in a very slightly different fashion, instead of curly brackets, use rectangular or parentheses, then the code will not work. So first line, in the first line, you have to define the Lagrangian. Can you check the Lagrangian that we derived is same as the Lagrangian written over here? M times L square multiplied by theta dot square by 2. Are you with me? This is the kinetic energy. Everyone understood this? The first part is kinetic energy. Looking at the chat window, any questions? Okay, now the second part is the negative potential energy. Can you see that we actually found out the exact same equation for Lagrangian? Now in the next line, you have to define what x is. X is the velocity and the displacement. Please note, displacement comes first, velocity comes later, and there is no comma or semicolon in between. There are no external forces. That's why Qi is 0. There are no internal forces. So this is 0. And this is actually the dissipation damping, but I have assumed K is equal to 0. So this term is 0. Right now, I'm not defining any parameters, but if you want, instead of providing the value of M, L, and G, you can define those as parameters and it would still work. In the next part, line number 16, this is the most important part. In line number 16, we are calling the function Euler-Lagrange.m. So we are calling this function Euler-Lagrange.m and we are supplying L, which is the Lagrangian, X, which are the states, Qi, which are the generalized forces, internal forces, damping, the dissipation, and parameters. And we are supplying, create a Matlab script, create a Simulink file, and call this block ODE1. Once again, Vf is the output of Euler-Lagrange function, and the arguments. Yes, you need to have Euler-Lagrange in your Matlab path. As a matter of fact, Euler-Lagrange, that function must be in the folder that you are using to generate the equations. Does that answer your question? So first VF is equal to this. You don't have to change this. So what you need to do is every time, here is what I would recommend. Copy this code in one folder, copy Euler-Lagrange in the same folder, and start modifying this code, and it will work just fine. Now, please note, this is a big piece of code. It takes time to generate the solution. So at this point, what I'm going to do is I'm going to highlight this all the way here. I would omit the semicolon, click and evaluate the selection. And then you will notice that this code runs. It will take some time. Are you with me so far? And then it will generate this VF function. That is the code that we need. Now it will also do a couple of things. It should create ODE1.m. Can you see ODE1.m? And I want you to open ODE1.m. Everyone open ODE1.m. Now this ODE1.m is the function, that is a differential equation written in the first order format. And for a minute, I want you to look at this code. Can you see that this code, this automatically generated code, is exactly the same equation that we wrote earlier? The only difference is we made sine theta 1 as theta 1. Can you see that this sine theta is approximated as theta? But this is the code. Everyone got this code? Were you able to get this code? All right, so please note, this is the code, or this is the piece of equation that we need to. When do we use each code? So just a second, bear with me. So from line number 2 all the way to line number 16, what we did, we used Matlab to derive the differential equation of motion. Everyone understood this? So Matlab derived the differential equation of motion. And this ODE1 is the differential equation of motion. Everyone understood this? The story does not end there. Matlab also created ODE1_block.slx. So please click on ODE1_block.slx. And you will notice, and I'm going to change my screen for a minute. So this also created a Simulink folder. So this is the Simulink block diagram. And if you double click on this block diagram, you will see that it created the Simulink code from ODE1.m. So can you see here that the Simulink code is generated? So you should have the Matlab code and the Simulink code. Are you with me so far? Now, how do we solve this? Please note, to solve, we are going to use Matlab again. So go to equation, run this first pendulum, and look at line number 22 to line number 30. Line number 22 to line number 30. In line number 22, we are providing the time span. So simulate the system from t time is equal to 0 to time is equal to 10 seconds. I'm supplying the initial conditions on theta and theta dot. These initial conditions are in radians and radians per second. These are the initial conditions in radians and radians per second. Then here I'm running this numerical integration. Please note, line number 26 will not change even if you have multi-degree of freedom robot. Later, you are plotting the solution. So can you see here in the line number 28, we are plotting the displacement, and on line number 30, we are plotting the velocity. So I'm going to run this code from line number 22 to line number 30, evaluate, and I'm going to share my results. So these are the results you should get. Are you with me so far? So you have displacement and you have velocities. Yes, the first half of the solution, first half of the code sets the equation. The second half of the code solves the equation numerically. All right, I'm going to give you 2 minutes to experiment and make sure that you got the results before I go on to Simulink. Everyone got the results? Please look at the Euler-Lagrange code and make sure that you understand that. Any questions here? Okay, I'm gonna run the first part of the code again. So highlight from here to here and run the code. Yeah, so ODE, so this actually would give you an error if ODE block already exists. So just to be on the safer side, just remove the previous ODE block and then rerun. And you will notice ODE block.slx will be created. Please observe here that this file just got created. Adriana, any questions? Did you get this? All right, now let's move on to Simulink. So as a matter of fact, at this point, if you want, you can actually delete ODE1.m, delete block ODE1 block.m, delete the only 2 equations. Yeah, hold on a second. This is the first degree of freedom system. We will gradually look at complex problems. So the comment QI says generalized forces, QE, our generalized forces and internal forces are 0, so it doesn't matter. Let me see, look at the comment. So QI, QE. So QI, QE. So this sequence needs to remain the same. So this is the function prototype. Now we need to use that one. Okay, now what you can do is, there is this pause 10. The reason for that is you can't run a numerical integration till the equations are formulated. So there is this pause for 10 seconds so that the equations get written. So you can go to, now you can actually run the whole code. Please observe, there is nothing here. There is nothing in the current folder except there are just 2 equations. Euler-Lagrange.m and equations, run this m, run this first underscore pendulum, run, and you would notice it will create two files. One is ODE1.m and the second one is ODE1_block.slx. SLX file is a Simulink file. Were you able to get the entire code running? Were you able to generate both the files? So now I want you to double click on ODE1 block SLX file. So this is the Simulink file. And I'm going to share that file with you. So I'll show you, this is how the file would look like. Now what we need to do is, we need to create the plot, or we need to solve this problem. So for that, I want you to go to the library browser. So can you see here, there is a library browser. Click on the library browser and the whole library would open up. It will take some time, but the library should open up. So now I'm going to show you what happens after you click on the library browser. So after you click on the library browser, you get this library. Everyone got this library? Okay. Now I want you to click commonly used blocks. Did everyone get commonly used blocks? Now I want you to look at the ground. Can you locate the ground? I have highlighted the ground in my Simulink library block. Everyone got the ground? Now drag and drop. Grab this, press your left mouse button and drop this into the Simulink canvas. Then grab this integrator. Can you locate the integrator? Since we have to integrate the equation, we need an integrator. Grab this integrator. Everyone dragged and dropped ground. For this problem, I'm going to go very slow because this is the first problem. Next time onwards, we will do it quickly. Now, drag and drop integrator. Everyone drag and drop integrator. And last but not least, click scope and drag and drop scope. So the three blocks that we are going to drag and drop into our canvas is ground, then integrator, and then the scope. Everyone understood this? You got these three blocks? Now I'm going to share my canvas. So if you look at your Simulink canvas, this is what you should have. You should have ground, you should have integrator, and you should have scope. Everyone has 1, 2, 3, and 4 blocks. All right, now we need to make connections. So ground will go to T. dy dt will go to S, 1 over S, because we are going to integrate. And we want to plot the result of integration. And since this is a recursive process, this Y needs to be fed from here. Now please attach the blocks the way I have attached. Please attach the blocks the way I have attached. Everyone got this connected? Now I want you to double click 1 over S. Please note, double click integrator. Double click integrator. After you double click integrator, then you will see this block. This is the internals of the integrator block. Everyone open the integrator. Now here we need to supply the initial conditions. Here we need to supply the initial conditions 0.1 and 0.1. These are the initial conditions. Click OK. And then go back to your Simulink folder or Simulink and then click run. Hit run. And once the simulation runs, double click on scope. Yes, the initial condition, the first initial condition is theta, the second initial condition is theta dot. Double click on scope. Double click on scope. And then you will notice that you have the same plot as earlier. So you would get the same plot as earlier. Are you with me so far? The only difference between this plot and the Matlab plot is we are plotting in degrees per second and this is in radians per second. So if you want everything to be in degrees per second, go to library block, grab the gain block and multiply this by 180 divided by pi. 180 divided by pi. Move this, add this gain block and attach this over here. So this gain block I'll show you how the gain block looks like. So bear with me for a second. So this is the gain block that you should see. Double click on the gain block and multiply this by again 180 divided by pi. And then, yes, I will open the integrator block once again and let me share the integrator block. Bear with me for a second. Now go back to the Simulink block and run. And now you would notice that, okay, yeah, we need to save this. We have to apply the changes and then run. And then you will notice that your plots from Matlab and your plots from Simulink would match. Any questions? Any questions? Were you able to integrator is the reason for integration is we have a differential equation. Differential means derivative. To find the solution theta dot and theta, we need to integrate that equation. So we need to integrate the equation. That's why we have to use an integrator block. Any questions? Any questions? Were you able to get the same? So the reason we have ground, because we want, as you can see, yeah, T is not connected to clock because we want the simulation time to be equal to the system time. That's why it is grounded. If the simulation time is different than the system time, then you can run that through a clock. So yes, so basically the system time, ground is the same time the solver time is fed into dy dt. So you will never change this. You will always connect T to ground. Any questions? Everyone understood that this is how you can use Matlab and Simulink to solve a simple problem. Are you with me so far? Okay, now let me share my initial screen and let me talk about some important aspects of the code. So in this particular code, this is a simple undamped pendulum. Now I want you to go to Euler-Lagrange and observe that in this code, there is an example for a projectile motion. There is an example for the projectile motion. So if you want to run this code, if you really want to run this code, if you want to do a projectile motion, here is what you would do. Say for an example, open a new script, copy from here, paste. If you want to open the rotary inverted pendulum, this is what you will do. Copy, paste it somewhere here. And if you want to run the double pendulum is a robot arm that we solved in last class. Copy, paste. So let's look at this code step by step. Everyone understood what we did? We copied the sample codes onto different script files. So first, I'm going to look at this code. I'm going to uncomment. So what I'm going to do is I'm going to uncomment. And observe what happens now. Select this code and evaluate the selection. The code would run and that will give you the differential equation for projectile motion. And observe, in this projectile motion, you have 6 variables: displacement in x direction, velocity in x direction, displacement in y direction, velocity in y direction, displacement in z direction, velocity in z direction. Can you see that there is g, m, displacement in x direction, displacement in y direction, displacement in z direction, and velocity in z direction. And as you can see, the total kinetic energy is summation of velocities in x direction, y direction, z direction. So kinetic energy in x direction, kinetic energy in y direction, kinetic energy in z direction. And you are subtracting the gravitational potential energy. And this code will generate the ODE1.m corresponding to this pendulum. Everyone understood this? Now look at the next part, rotary inverted pendulum. In the rotary inverted pendulum, uncomment from line number 2 to 13. So uncomment. And in this, you have I, you have M, you have length, you have R1, G, A1, DA1, BE, DBU, and tau. And what you can do is you can select and run. And it will generate the rotary pendulum ODE block underscore SLX and rotary pendulum ODE.m. So these are the differential equations of motion for rotary pendulum. Go to the next code, which is for the double pendulum. And for double pendulum, also uncomment. And then you can evaluate and run. And please note, these are the differential equations for the double pendulum or 2 degree of freedom robot arm. Now, let me quickly tell you what this pendulum is all about. So you have the kinetic energy of the first mass. You have the kinetic energy of the second mass. Then you have the potential energy of the first mass, and you have the potential energy of the second mass. So notice theta 1 dot square, and this is the kinetic energy of the first mass. This is the kinetic energy of the second mass. Then what you have is you have the potential energy of the first mass and the potential energy of the second mass. And once you have Lagrangian formulated, you can find out the equations of motion. And the next part is just you need to replicate what we have done over here, which is numerically integrating the equations of motion, or you can use the Simulink block to integrate inside the Simulink environment. Everyone understood this? So as an exercise, here is super duper important. If you don't practice, you would forget. So note, I have this untitled 5, untitled 6, untitled 7. So please numerically integrate and generate the plots the way we have generated for a simple pendulum. Please numerically integrate and generate the plot for these the projectile motion, inverted pendulum, and the double pendulum, so that when we start the robot problem next time, you would be fairly familiar with this problem. So this is the basis on which we are going to use and derive the differential equations of motion. Please understand, on Thursday, since I'm out of town, my recent PhD graduate would teach the class, and he would be talking about something called as path planning. It's a very simple concept based on the regression and how to go from point A to point B. So there will be a class on Thursday. You would get, again, it would be a Zoom class, and you would receive an email to log in to the Zoom class. So I will teach the next class next Tuesday, but we will be focusing a lot on deriving the differential equations. Yeah, actually, I already moved homework 4. If you look at the homework 4, unfortunately, I don't have office hours today as I'm traveling. Okay, you want me to move homework 4? I will go ahead and move homework 4, no problem. Anything else I can help you with? If you have any questions, I would be happy to answer. And okay, let me go ahead. No, we have not learned how to do homework 4. That's why I'm going to postpone homework or assignment 4. I will go ahead and postpone assignment 4. Yes, I will postpone assignment 4 to November 4. Can you make a review? Yes. No, I need to work out the problem in detail. So I would work out the homework 4 problem in detail. Yes, I completely understand. This is a little confusing. So I'm going to work out problems again in next class and on Thursday's class. So you can work out homework 4 finish the first part of the homework 4, and I would help you with the second part of homework 4. So please go ahead and work out the problems. Any questions? So please work out example on projectile motion, example on rotary inverted pendulum, and example on double pendulum. And try to generate the plots using the Simulink and try to generate the plots using Matlab. And I'm going to stop here, but I would be happy to answer any questions you may have.